Hey there, I'm Dirk, representing IBM from Toronto, Canada. First off, thanks to Carly and the Gartner team for putting this event on and having us as guests. I'm really pleased to be telling IBM's story here. The big challenge organizations face today is how can their people ask new questions against all their data? Our position at IBM is that users need an environment that provides governed access to data through a variety of tools designed for different user types. These are the design principles for Cloud Pak for Data. It includes a breadth of capabilities covering all the stages you'll go through to build data assets like machine learning models and dashboards. One of the keys to successful analytics projects is combining domain expertise in the problem space with data wrangling and data science skills. In the Watson Studio portion of Cloud Pak for Data, we've developed new tools designed to help business users make sense of their data and take an initial cut at some of the data science work involved in building models. At the same time, Watson Studio also includes tools for data scientists, which they can use to pick up where the business user leaves off, and ultimately they can go back and forth with the business user working together in the same project. Based on the Knowledge Catalog service, all the data assets that you build in Cloud Pak for Data are under a governance regime, which enables both trust and further self-service. For example, all the work that you and your team did as you built a training data set and a new machine learning model is captured as a breadcrumb trail. On the trust side, this provides accountability for cases where you need to explain it to a regulator why you approved a certain loan. On the self-service side, another analyst can find your model and training set as they quote-unquote shop for data in the asset catalog. And rather than reinvent the wheel, they can reuse some of your work. I hope you enjoy what I've got to show with Cloud Pak for Data a little bit later. It's available both as a service on the IBM Cloud and as an installable offering on-prem or other clouds through Red Hat OpenShift. Thanks.
So here we are in Cloud Pak for Data, where we have a full range of analytics tools at our disposal. We're going to move into the project I've set up for this life expectancy prediction exercise, where you can see I've uploaded the World Health Organization and World Bank data sets for the United States and a number of other countries. The first thing we'll do is get our bearings and check out the data. Right away, we can see some challenges. There's a second header row, which will cause problems for all kinds of tools. There are a number of empty columns, which will clutter up our view of the data, and there are many rows of actual mortality data, which we need to remove as that will skew any model training on life expectancy. We'll take care of the initial filtering in the refinery tool, where we can get rid of this excess content with just a few clicks. The profile tool is very useful here as it shows values we can filter on without having to go back and forth between windows. I'm now going to save and run this transformation. This creates a new file where we can focus on getting rid of the data we don't need. While we've gotten rid of excess data, we should start exploring the data set a little bit deeper. We can quickly see a few issues here. Even though this data set is published by a reputable international organization, there are still problems. This is totally normal. The numeric field is empty for some records, while we can see data in the display field. We can fix this really easily in the refinery tool. There are also some oddities in the year field, a number of GHO codes of date ranges instead of representing discrete years. This can be a bit tricky. This is actually a good example where you, as the business analyst, could hand off to a data wrangler person who knows SQL or Python and can split out the rows. I've done this in a Python notebook. Check out how the flow continues without problems. You can take the notebook output and continue refining the data in the refinery tool. Here, we'll get rid of all the rows outside the 2000 to 2016 range. After some further filtering, we're ready to pivot the data, which we need to do so that we can start training our model. In order to train our predictive model, we need data where each row represents the values for a country for 1 year. We've got a few options for the pivot operation. We can have our programmer colleagues do this in a Python notebook, like we did before, or we can use the Modeler Canvas tool. This is available under the base entitlement in the cloud version of Cloud Pak for Data, and also available as an add-on in the on-prem version of Cloud Pak for Data, which I'm using here. The World Bank data needed a bit less cleaning, and we took the same filtering and pivoting steps with it. The refinery has a simple join tool, which I use to combine the World Health Organization and World Bank datasets. I also used the refinery to create the training and test data sets, keeping data for 2015 and 2016 in a separate file. Here's a quick look at the modeler canvas tool I just mentioned a couple seconds ago. This represents a left-right flow of data where each of the nodes represents some kind of action imposed on the data. You can see the pivot operations for both the World Bank and World Health Organization data, and then there's a merge operation which does the join, and then the data is saved into the separate files. Now that we have the combined file, where all the indicators are organized by column, it's much easier to browse the columns to get a sense of what might have predicted value and what doesn't. I've also repeated the data preparation process for data from 14 other countries so that we can have a bigger sample size. And scrolling through the data, we can see a number of columns with mostly null values. Those won't be useful. For the more populated columns, we need a better approach. The profile tool gives us a nice breakdown of the data. We can see distributions and standard deviation, so at a glance, we can skip over a number of features that very obviously won't help us with our predictions. But when something visually interesting shows up, we can check the description to see if there's applicability. This is the classic combination of using applied stats plus domain knowledge to work on feature selection. Simple dashboards also help the feature selection process, as we can quickly graph features against life expectancy to observe any possible trends. Here, I've plotted the values of 4 different columns for the years 2000 to 2016. They've all got something resembling the very slight upward slope of life expectancy at birth. In fact, the slope of urban population percentage of total population is almost identical. The lines overlap.
Now that we have a training data set, we're ready to start actually training our life expectancy predictive model. Normally, this is very much an iterative process where you start with educated attempts at figuring out what features to put in your training data set, and then you experiment with different machine learning modeling approaches. For many line of business users, understanding the nuances of feature engineering and model selection can be really overwhelming. So with this in mind, IBM has been developing a wizard-based tool for training machine learning models called AutoAI. You begin by feeding it your training data set. So we're starting with the US only data set, even though we do have that more full data set with more countries that we saw earlier. We'll now indicate which column we're predicting. You've got the World Health Organization life expectancy at birth code listed here, and we'll select it. Before saving the settings and beginning the training, we have the opportunity to automate how the training data can be split. By default, there's a 10% holdout data split, which is fairly normal, and we'll keep that. Note that we have already omitted the 2015 and 2016 years from the United States data set on top of this, as per the request from Gartner. Once we start the experiment, AutoAI presents a visualization of the state of the model training. The first thing we see is the training data set being broken up into folds and a holdout data set. This facilitates 2 approaches for validating the model, which might seem redundant, but it's actually quite useful for different circumstances where a model might look good in one validation approach but poor in another. On top of the feature selection we did earlier, AutoAI will now map out the different model training pipelines it estimates will yield the most accurate models. There are many ways to track progress here depending on the perspective you want to see. Once AutoAI has finished generating the model pipelines, you can now evaluate the models to see which one suits you best. The pipeline comparison view presents the most common error metrics used to evaluate model performance. The results are all presented on a leaderboard, making it easy to distinguish between the competing options. Before we began the model training process, I mentioned there were 2 model validation approaches being used. They're cross-validation and holdout. You can toggle between the 2 to see the difference in model performance. Part of the evaluation process is looking deeper at the individual candidate models to get a clearer picture of your modeling experiment. From the progress view, you can see that half the candidate models had some feature engineering in their pipeline. Part of what AutoAI does is evaluate the training data and then apply some manipulation to features that it deems needs improvement. In keeping with the iterative nature of model training, AutoAI also provides a report on the relative importance of different features, which can sometimes take away from model accuracy. So this model yields what looks like fantastic results. The root mean squared error is a tiny 0.092 for our best model. That basically means that the life expectancy prediction is off by a little over a month, which is incredible. But as we look over at the R squared number, it's very close to 1, which tells us that the model is likely overfitted. And this is likely because our sample data set is only 15 rows. To show what the 2015 and 2016 US rows will yield as a life expectancy score prediction, we can go to the deployed version of our model, and we'll discuss deployments in our next section. And here we can run a test score against the live running model. Here we have scoring results for 2015 and 2016. And they're both off by 2 years, which is much worse than the error margin we saw earlier in the training. Again, this is because of the small sample size. The candidate models generated by AutoAI can be deployed using the Watson machine learning service. They can also be downloaded as Jupyter notebooks, which is useful for any data scientist counterparts providing assistance to the business analyst. In addition, along with AutoAI, CloudPark for Data features other model building tools. Jupyter Notebooks and Jupyter Labs, which we saw earlier. These are the standard tools for programmer data scientists today. We have a modeler flow canvas. We saw the visual flow tooling earlier, and in addition to the data preparation widgets, there are a host of different machine learning modeling techniques available here as well. This canvas tool is great for people who are savvy with applied stats but aren't comfortable programming. And finally, we also include RStudio. There is still a strong contingency of applied stats people working in R, so it makes sense for us to serve this community as well. Back to the modeling effort, I've already run a model with data from many more countries, but I've only included a smaller set of features, which we think might have predictive value. You'll notice that the root mean squared error is about 3 times higher, but you'll also notice that the R-squared number looks much healthier and isn't suggesting overfitting.
Now that we've created a model, we're ready to do something with it. CloudPark for Data features a model deployment service called Watson Machine Learning. It's a scoring engine for machine learning models and supports a wide range of frameworks. This means that regardless of whether your data scientists are using open source model frameworks in their Jupyter notebooks or if you're playing with AutoAI, whoever is managing model operations for your organization, they have a consistent management plane for all these models. From AutoAI, when we save the candidate model we've chosen, it's pushed to the Watson Machine Learning service. While AutoAI is really all about experimenting with the model training process, we're now going to be focused on the operations of the model. As we look at our project, we can see our newly published model. From here, we can promote the model to the deployment space, which is where you can manage your models. For our deployment, we'll choose the online form factor. This is the best choice for situations like when you have a web app where there will be individual scoring events. You can deploy your models as batch services as well and associate them with more robust hardware configurations. And here's our deployed model. It's now ready to be added to your application. We provide code snippets to make embedding the model easier. Also, here's the model testing tool we saw earlier. Let's say you retrain the model, as you have newer training data that better reflects current conditions. You've got some active deployments of your model, and if you want to make sure your application is delivering the best predictions, you have 2 choices. You can deploy new versions of the model in your deployment space and change your app to point to the new deployment. Or you can replace the existing deployment with the new version of the model.
In CloudPark for Data, we have a model operations console called Watson OpenScale. It's designed to provide your model operations people with dashboards and tools to ensure that your organization's models are healthy. Here, we can see our life expectancy predictive model alongside a few other models. Let's take a look at the dashboard for our model. Things aren't healthy. Remember that this is the first model we created in AutoAI, where we only use the US data. Those quality metrics we talked about during model training are still relevant once the model has been deployed. You can set alerts for when the model dips below your quality thresholds. A big challenge for people who deploy models is the concept of drift. The reality that we're trying to model is constantly changing, which means our predictions need to be constantly monitored. I have submitted the rows from the 14 other countries to the model we trained with the US data. Clearly, there's drift, which shouldn't be surprising as every country has its own patterns in their data. So now we get a recommendation to retrain the model. Another contrast between model training and managing model deployments is examining the impact individual features have on the model. Here, we're looking at the prediction for life expectancy against one of the initial US models that we built, where I submitted data for 2016. When we trained the model, the system calculated that in general, the current health expenditures per capita and consumer price index have the most predictive value. Now, we see that urban population percentage and urban population growth are the most impactful factors for this particular prediction. There is good potential for interesting analysis, as you can submit hypothetical numbers for the indicators we put in the model and see how the model responds. This is a really useful exercise when trying to forecast policy impacts. Now, this is a regression model, which means that we're predicting a continuous number, which makes total sense because it's age. For classification models, OpenScale has an additional interesting feature called contrasting explanations. Here, we've got a model that recommends whether or not to approve mortgage applicants. We can see the factors that contributed to this particular application being turned down. But at the top, we can also see which factors can be adjusted for the score to flip to recommending a mortgage approval. Most significantly, the model is suggesting this person needs to move out of his parents' basement. Coming back to our model, after iterating on the features, I trained a much better model using the data from a number of other countries in addition to the United States. The root mean squared error is down to roughly half a year, and the R-squared is healthy but not too high, so it's likely not overfitted. For this model, health spending clearly has the strongest predictive value. We're also seeing educational attainment, drinking water quality, and some economic indicators having some predictive value. There were many minefields in this data. Going beyond even the cleansing and preparation, the sample of years and countries reflect a very specific context in the overall question of life expectancy. The countries were all in the West, and indicators that have been long associated with higher life expectancy, like access to clean water, medical care, and good nutrition, are all at a high base. So really, this becomes an exercise in predicting what could further increase life expectancy in an era where we already have historically high numbers. As I started processing the data and evaluating indicators, there were a number of them that trended quite closely with the life expectancy at birthline. Some of them were surprising. For instance, body mass index had almost the exact slight slope upward. Intuitively, we know that on an individual basis, BMI and obesity are bad indicators for life expectancy. Practically speaking, given life expectancy continues to go up, there must be other factors acting as a powerful counterweight to what one would expect are opposing trends. So based on a combination of domain knowledge and data science work, my conclusion is that the following indicators have the biggest impact on life expectancy: current health expenditure per capita, educational attainment, urbanization. Now, all of the widgets that we've seen today are under the governance regime in Cloud Pak for Data, and the more refined assets can be promoted to the enterprise-wide data asset catalog, as we can see here. This means that people can search for data assets that are of most interest to them, and with our business glossary, use common business terms. So my concluding thought here is that there are many roads to the model development mountaintop. For the customers I visited with, I've seen a massive variety of the blends of different personas doing data science. For example, some shops rely almost exclusively on database technologies using in-database machine learning capabilities, and then others rely on visual modeling entirely. So the key for us is to provide alternatives for all these personas that still enable them to take advantage of each other's work and build on it, and that we can share these assets in an enterprise-wide catalog. Finally, integration with the rest of the data infrastructure is critical for machine learning development, as, after all, models are a premium data asset, and having a holistic view of the end-to-end data architecture is vital. Thank you very much.